Hello, everyone. Welcome back from Brazil, and welcome to Georgia Tech Graph Theory Seminar, I think, which is the 18th stop of the Around the World relay in Combinatorics. So today we are very happy and excited to have Professor Geelen from University of Waterloo, and he will talk about homomorphisms and coloring for graphs and binary matroid. Professor Geelen, please.
Okay, thanks, Zhiyu. Thanks very much for the invitation to speak in Atlanta and for the opportunity to participate in the Around the World Combinatorics relay. Before I get started, I just want to clarify that this is a drawing of a baton pass in a relay, not of one man bashing another one with a stick, which apparently my wife thought it was when she saw my picture. So what I'm going to talk today about is just mainly conjectures that I really like. So that's the main focus of the talk, is to tell you some conjectures that I really like. And there are also one or two new results, and they're joint with Peter Nelson and Raphael Steiner. So they're results we proved this year. Okay, so the basic question that is motivating everything in this talk is the question of what structure do you have in a graph that has huge chromatic number? So that's basically what we want to know. And there's been a huge amount of research on that question over the years, but in fact, we don't really know that much, I don't think. So in particular, we don't know how to distinguish between a graph that's 3 colorable and a graph that's not 1,000 colorable or not 1,000,000 colorable, right? So if I give you a graph and I ask you, is it 3 colorable? Even if you gave me a graph that wasn't 1,000,000 colorable, I wouldn't be able to tell you that it wasn't 3 colorable efficiently. So this talk's got nothing to do with the second question as such, because I'm not going to be talking about anything algorithmic, but I'm thinking more about structural things. And I'm also not going to be shedding really much light on the first question either, but that's what motivates the talk. And I will actually finish off with a conjecture that I think is sort of in the direction of the first question, at least. So there is going to be some partial answer to the first question, at least a conjectural one. So the very first thing you think about when you try to color graphs is lower bounds, and the most obvious lower bound you get, it comes from complete graphs. So if you've got a complete subgraph, you have to color all those vertices differently, so the chromatic number of the graph is at least the clique number. But there's no qualitative relationship between these two parameters. There are graphs that don't have a clique of size 3 and yet have arbitrarily large chromatic number. And that's a classical theorem from Tut in the 1940s. 10 years or so after that, Rödl proved an even sort of more devastating negative result, that you can have graphs with arbitrarily large girth and arbitrarily large chromatic number. And so that says that if I've got a graph with huge chromatic number and I look at a constant number of vertices, I'm not going to be able to see that the chromatic number is large. When I take a constant number of vertices, I might just see a bipartite graph, regardless of which subgraph I choose. So that's sort of really one of the fundamental difficulties when you're dealing with chromatic number. So actually I should say that when you look at these results, so the first result due to Tut has this is a very clever construction of triangle-free graphs with large chromatic number. And Erdős's proof is probabilistic. There's a number of other constructions for triangle-free graphs with a large chromatic number, and they're also very clever. And it was a lot of years before we had constructions for graphs with arbitrarily large girth and chromatic number, explicit constructions. So for a long time, Erdős's probabilistic method was really all we had for getting graphs with arbitrarily large girth and chromatic number. So you get the feeling when you try to work with these things that these kinds of graphs are really special. And there's a beautiful theorem due to Rödl from the late 70s that basically says that these graphs aren't special, they're ubiquitous. So this is a nice connection to Atlanta. So Rödl proved that every graph with huge chromatic number contains a triangle-free subgraph with large chromatic number, right? So triangle-free graphs with large chromatic number are ubiquitous. They exist in all graphs with huge chromatic number. I only learned this, so this is a theorem from the late 70s, but I only learned it about 2 years ago, and I was kind of embarrassed by that. And then I looked at the list of citations for the paper, and it turns out that it hasn't been cited in any of the sort of standard textbooks in graph theory. So I think in a lot of ways it's an overlooked theorem. It's a beautiful theorem. What makes it even more surprising that it's an overlooked theorem is the fact that the proof is so nice. If this was a 50-minute talk, not a 40-minute talk, I would give you the proof. It's a really great proof. But it's a 40-minute talk, so I don't have time to go into the proof. But I would highly encourage you, if you don't know the proof already, to look it up. It's lovely. Another thing I really like about this theorem is that it's got an enormous number of connections to other open problems in graph theory. And it also extends to a whole bunch of different things. So you can define chromatic number for directed graphs, and you can make a directed graph analog of this. There's a nice conjecture about induced subgraphs and chi-boundedness that's related to this. You can think about infinite graphs and infinite chromatic number, and if you're just thinking about infinite chromatic number, you don't end up with an interesting question. You just end up with something that turns out to be equivalent to Rödl's theorem. But if you think about uncountable chromatic number, you end up with a nice conjectures. And also for binary matroids, you end up with really nice conjectures. And we'll be spending a lot of time talking about binary matroids, so we'll see that direction. The most obvious way to go from Rödl's theorem, most obvious way to try to generalize it, actually is this conjecture of Erdős and Heinel, and they posed this well before Rödl proved his theorem. I think this was maybe from, I think, the early 70s or late 60s. So they conjecture that every graph with huge chromatic number contains a subgraph with large girth and large chromatic number. So if this is true, that would say that the graphs with large girth and large chromatic number are ubiquitous. So this seems like quite a difficult conjecture. So there's been no real significant progress past Rödl's theorem. You can get rid of the triangles, and the natural next question is, can you get rid of 4 cycles? And there's hasn't been any progress on that I know of. I think actually that, I'm not at all sure of this, but I suspect that it might be actually easier to get rid of 5 cycles than 4 cycles. So I think that might actually be the natural next thing to try, although I haven't had any success with that myself. So thinking about the conjecture made me wonder, what happens if we replace the subgraph containment operation with a different kind of containment operation? And more specifically, what if we think about homomorphisms? So to take a homomorphism of a graph, you're identifying pairs of non-adjacent vertices and then simplifying. I'm only really interested in simple graphs. in this talk because chromatic numbers are about simple graphs. Right, so you identify pairs of non-adjacent vertices and simplify. If I do that, I don't get that graph. I get that graph minus this edge. But you say that H admits a homomorphism into G if there's a homomorphism of H that's isomorphic to a subgraph of G. Right, so if I take this homomorphism, I get a subgraph of G. So H, in this case, H does admit a homomorphism to G. And this behaves a bit like subgraphs, right? So if H is a subgraph of G, then the chromatic number of H is a lower bound on the chromatic number of G. But that's also true if H admits a homomorphism into G. And the reason that's true is when you're taking a homomorphism, you're sort of conceptually just restricting coloring. So when I identify two non-adjacent vertices, from a coloring point of view, I'm just forcing those two vertices to get the same color. So you get this. And so it works so homomorphisms work very nicely hand in hand with colorings. And so it's kind of a natural thing then to go back to those conjectures and wonder whether you can replace subgraph with homomorphism. And if you think about it a bit more, then it turns out that you get something far stronger than a qualitative characterization for chromatic number. If you're willing to use homomorphisms, you get a precise characterization of chromatic number. And this theorem is really spectacular. It's an amazing theorem. It gives you an exact characterization for chromatic number. It looks a lot like a co-NP characterization for an NP-hard problem. So it looks a bit too good to be true. So the result says that if you've got that a graph has chromatic number at least T, if and only if you can obtain it from copies of the complete graph on T vertices by applying certain constructions that I've drawn here and applying homomorphisms. It turns out it's not a co-NP characterization, and P is not necessarily equal to co-NP, but it looks amazing.
Jim, I have a question.
Yeah.
I find this also amazing, and I've tried using it in the past. I found it very hard to apply for any sort of problem that I was interested in. So I'm just wondering if you know if this has actually been useful in various ways.
Well, that's exactly my next comment. That as spectacular as this result is, I don't know of any applications whatsoever, except you can prove that a graph's bipartite if and only if it has no odd cycle, right? I mean, that's incredibly underwhelming. And that's the only thing that I know that you can prove with this. And it's a pretty bad proof. It's a very easy theorem to prove, and it's an incredibly beautiful theorem, but it just doesn't have any applications. It's slightly frustrating. Thanks for the question. Okay, so let's go back to this conjecture of Rödl and Heinel. So the Rödl-Heinel conjecture is saying that if you've got huge chromatic number, then you contain a subgraph with large girth and large chromatic number. So what would the natural thing to do, what would be the natural homomorphism analog of that be? You would say, I've got a graph with huge chromatic number. I want to say that there is a graph with large girth and large chromatic number that admits a homomorphism to it. Right, so it's sort of telling me, it's showing me that it's some graph with large girth and large chromatic number that's showing me that my chromatic number is not too small. And it turns out that you can, in fact, prove such a theorem. But amazingly, you get a much stronger theorem. So if you give me the girth you're interested in, and I've got any graph, I can find a graph with that girth that admits a homomorphism into my graph, and I don't have to give up anything in the chromatic number. you can keep the original chromatic number. So there's no going from huge chromatic number down to large chromatic number. You just keep the original chromatic number. So this is a nice generalization of Erdős's large girth, large chromatic number theorem, because you can apply this to any graph. So when we proved this, we were sort of pretty amazed that it's like a nice graph theory theorem, and it's so pretty. So as soon as you prove a pretty graph theory theorem, you're pretty sure that someone's proved it before. And so we emailed Noga Alon and asked him if he had seen it before, and in fact he had proved it before himself. But he, as far as I know, I believe he hasn't published the result. He just noticed that it was true. Now we proved it using Erdős's probabilistic method, but Noga has an explicit construction for these things. So he used bipartite expander graphs and proved it that way. But let me quickly go through the probabilistic construction. It's quite nice. So the idea is you take your graph and you lift up each vertex into what I'll call a fiber. So you lift each vertex into an n-vertex fiber, and then I can put the edges in. So these vertices here are going to map to this vertex, and these vertices here will map down to this vertex in the homomorphism, etc. And so where I've got an edge in the graph, I'm allowed to put edges between the two corresponding fibers. And I choose those each independently with probability alpha over n. And I'm thinking of n here as being something huge, and I'm going to choose, and I'm going to play around with alpha so that my graph has the properties that I want. Now, we need to get rid of short cycles, and basically what you can prove is that the number of short cycles depends only on the graph G down here and alpha, and doesn't depend on n. Right, so I can make this graph enormous, and this just doesn't depend on n, and that means that when I'm deleting a few vertices to kill these few short cycles, I'm still going to have these huge sets left. And now to control the chromatic number, we're going to think about stable sets. So basically what the idea is as follows. You think about a coloring of the big graph. And when I color the big graph, I look at this fiber, and I ask myself, what's the majority color that I've used in that fiber? And I associate that color with the vertex of the original graph. And that gives me, in general, it will be an improper coloring of the original graph. And what you want to say is that with high probability, that improper coloring is a proper coloring. And for that, what you want to say is that if I take a large fraction of the vertices in U and a large fraction of the vertices in V, there's always going to be an edge between them. And you can force that just by pushing this alpha up. Like for whatever fraction you want, you just push alpha up and you will get that. And so that's it's a very simple theorem, but that's the proof, right? And Noga explained in an email. So actually, I emailed Noga the question, and he replied in half an hour with basically like a long one-page response explaining how to do this constructively by putting in bipartite expanders here. It was very impressive. I mean, when I get an email that's like slightly technical, it always takes me half an hour to go make a cup of tea and come back and start thinking about it. So to get a response in half an hour is quite incredible. Okay, so that's it for graphs for the moment. So now I'm going to move on to binary matroids. So binary matroids are basically represented by, so a rank R binary matroid is represented by a binary vector of length R. Every element is represented by a binary vector of length R. And being simple means that no two elements are represented by the same vector, and also you don't have the zero vector. So there's 2 to the r minus 1 different vectors you can choose from for an element. And so every simple rank R binary matroid is going to be a restriction of the matroid you get, the rank R matroid you get, by taking all 2 to the r minus 1 distinct binary vectors, non-zero binary vectors of length r. And that matroid is the projective geometry. If you take that, all of the vectors, you get what's called the projective geometry. And the way we think about binary matroids, in this talk at least, is as a set of points in a projective geometry. So I take the rank R projective geometry and I take a subset of the points there. Now, a binary matroid is affine if in the projective geometry I can find a hyperplane that doesn't contain any of the elements of my matroid. Okay, so that's what it means to be affine. I can find a hyperplane in the projective geometry that's disjoint from my matroid. And Tut proved that these correspond exactly to bipartite graphs. Being an affine for a binary matroid is exactly corresponding to being a bipartite graph, in the sense that a binary matroid is affine if and only if it doesn't have an odd circuit. And this enables you to define chromatic number for binary matroids. And this was defined by Crapo and Rödl, and they call it, well, actually they call it critical exponent. It's since been changed to critical number. So the critical number of a binary matroid is the minimum number of affine matroids needed to cover it. So in terms of graphs, you'd be basically asking, how many bipartite graphs do I need to cover my graph? So we'd all be familiar with the idea that a graph's four-colorable if and only if it's the union of 2 bipartite graphs. And more generally, the number of bipartite graphs needed to cover a graph is going to be something like log the chromatic number. Right? So the critical number of the cycle matroid of the graph will be the log of the chromatic number of the graph with appropriate rounding. So from a point of view of the questions I'm asking, for graphs, it wouldn't matter whether I was using this critical number or chromatic number, because I'm asking what happens when something's huge. And since these two things are qualitatively related, it doesn't make any difference which parameter I'm thinking about. And if you look at Rödl's theorem, there's a very easy analog of that for binary matroids, and it's a conjecture I really, really like. So the conjecture is that every binary matroid with huge critical number has a triangle-free restriction with large critical number. I think that's a very nice conjecture. And so what does triangle-free mean in this context? So it basically means you don't have 3 points on a line, or equivalently, there's no 3 vectors summing to 0. And this is a direct generalization of Rödl's theorem, because if you take the cycle matroid of a graph, the critical number is related qualitatively to the chromatic number. Right? So this is a direct generalization of Rödl's theorem. I feel I should point out here that there's, I think, a lot of scope for work of this kind, where you take theorems in graph theory, particularly relating to things like chromatic number, and look at the corresponding analogous result in binary matroids. This was reasonably popular in the 70s, but hasn't been done for a while. And there's been an enormous amount of progress in graph theory over the years. And so there's a lot of scope for taking the work that's been done since then and and asking what the analogous results are for binary matroids. Peter Nelson's been doing this to great success over the last few years, but I think that there's so much opportunity there that it's kind of surprising that other people haven't really joined in to look at that. I think there's really a lot of nice results to be had in this direction. And one reason I think that maybe it's slightly hasn't been looked at as much as it could have been is because typically when you do generalize from graphs to matroids, it doesn't take you too long to figure out what the right statements might be, but you typically don't end up with generalizations. You typically end up with analogous results. And in this case, you get a direct generalization, so it's particularly nice. But very often you end up with analogous results. Surprisingly, the proofs are often much easier for the matroid setting than the graph setting. And that's because the projective geometry has that much extra symmetry than graphs have. There's just so much symmetry in a projective geometry, and you can often utilize that to great effect. Sometimes the problems are way harder, but that's also extremely interesting because they're usually relating to interesting problems in other parts of mathematics. So I think it's really a great area to work in. Okay. So let's move on to homomorphisms for binary matroids. And these are just the same thing as you would have for graphs. I mean, it's like you think about homomorphisms for graphs briefly, and then immediately you get something working nicely for binary matroids. So when you take a homomorphism of a graph, you're identifying a pair of non-adjacent vertices and simplifying. One way to say that is that you add an edge between two non-adjacent vertices and then you contract it and then simplify it. So I take my binary matroid, I got the points in yellow there that are part of my matroid, and then I got this point that's not part of my matroid. So what I'm going to do is I'm going to put a point there and contract it. And what contracting means is you project from there onto a hyperplane that is disjoint from it. So in this case here, I get these, I'm basically projecting these three lines down to points, and since each of these lines contains a point of my original matroid, I would end up with these 3 points occurring in the homomorphism. So that's a homomorphism. And you say that N has a homomorphism into M if there's a homomorphism of N that's isomorphic to a restriction of M, which is exactly the same thing that you would do for graphs. And also the same as for graphs. The critical number of the matroid M is at least the critical number of N if there's a homomorphism from N into M. Okay. So that's nice. And it turns out that you can actually use this notion of homomorphism to give an alternative definition for critical number that is quite well motivated, I think. So for graphs, your universal objects are complete graphs, and the one way to define the chromatic number of a graph is it's the smallest t such that your graph admits a homomorphism to kt. For binary matroids, the critical number of a binary matroid is the smallest t so that your matroid admits a homomorphism to the projective geometry of rank t. So that's like the most natural thing you could possibly imagine. Like once you see this definition of chromatic number, this is incredibly natural. And what's more, the same proof for Hayos's theorem just works for binary matroids. You just do exactly the same thing and it just works. So a binary matroid has critical number at least t, if and only if you can obtain it from copies of the rank t projective geometry by certain Hayos constructions and homomorphisms. And again, this theorem is equally as useless. So it's just like graphs. Okay, so what we did is we proved the natural analog of the theorem I showed you earlier for homomorphisms. So if you have a binary matroid M and an integer G, then I can find a binary matroid N with girth at least G. That just means you have no cycle of length less than, no circuit of length less than G in the matroid N. N has to have a homomorphism to M, and the critical number of N is the same as the critical number of M. So this is the exact analog of the theorem that I stated earlier. In this case, they're just analogous. I wouldn't imagine one could prove either one from the other. This is one of the instances, however, where the binary matroid version is easier than the graph version. So you do the same kind of proof. You think about what a homomorphism, like lifting by n dimensions, would look like, and there's a sort of a unique universal object that you can construct that would have a homomorphism. So a maximal object that has a homomorphism, it's unique. And then you choose the points from there uniformly at random. And the big difference between the binary matroid case and the graph case is that short circuits just disappear. So in the graph case, you just don't get many short circuits and then you delete a few vertices. In the binary matroid case, they just don't exist. So it's slightly easier. So the random object you construct has large girth and large chromatic number, or large critical number. And that's the result. Okay. So moving on, let me tell you, I think, one of my favorite conjectures at the moment. And I'll just say the conjecture and tell you what I like about it afterwards. So I've got a binary matroid with huge critical number. Then there's a graph G with large chromatic number that admits so that the cycle matroid of the graph admits a homomorphism to my matroid. So what this is saying is that from a qualitative sense, binary matroid critical number is really just graph chromatic number, which I find really, really pretty. So the difficult thing is, like, how do you get the graph? But actually, I can tell you the graph. Even though I can't prove the conjecture, I can tell you the graph. So without loss of generality, if this conjecture is going to be true, you take a certain Cayley graph defined by the matroid. And that Cayley graph is defined as follows. So you take a usual matrix representation of your matroid, your binary matroid. So it's a rank R matroid. The vertices of the graph are all binary vectors of length R. And two vertices are adjacent if their sum is a column of the matrix. Right, so it's just the Cayley graph you get with this as a connection set. And it's easy to prove that this matroid admits a homomorphism. The cycle matroid of this admits a homomorphism. And basically what's going on here is the following. The projective geometry has, well, roughly these as elements, except this has got the zero element in it as well, but let's forget about that. This has got one extra element, the zero element, but the other elements are all elements of the projective geometry, and these vertices are going to get mapped to the elements of the projective geometry, and when you do that mapping, the elements of the matroid just get mapped onto the elements of the matroid. So this is actually quite straightforward. And it takes a bit more work to prove that the chromatic number of this graph is bounded by 2 to the critical number of the matroid. But that's also pretty straightforward to prove. The previous conjecture is equivalent to proving that the critical number of the matroid is bounded by some function depending only on the chromatic number of the graph. And I find this fascinating. If the graph's bipartite, I can tell you that the matroid is affine. That much is really easy. So I thought for quite a while that 3 coloring was going to be the crux of the problem. But it turns out that's not the case. In the late 80s, Charles Payan proved that if the chromatic number of the graph is at most 3, then in fact it's at most 2. So if the graph is 3 colorable, it's 2 colorable, and then the matroid's affine, which is kind of surprising. And this interest in these graphs in the 80s was really coming from the Cayley graph community. So they were interested in these things. So these particular kinds of Cayley graphs where you're dealing with the binary vectors, these things are called cube-like graphs. And there was a fair bit of interest in those. I think Charles Payan, I'm not sure about this, but I think he might have been a student of Francois Jaeger, and Francois Jaeger had several conjectures about these things.
Oh, they were colleagues. They have the same age.
Oh, they're colleagues. Thanks. I just noticed that they worked on a lot of the same things, but they were colleagues.
Right.
Thanks. Okay, so now I think that the real crux of this conjecture is going to be what happens if the graph's 4 colorable. So that's what I'd love to see a proof of. If this graph is 4 colorable, can you bound the critical number of the matroid? I think if you can probably, I suspect if you can do that, you can probably solve the conjecture in general. So now I just want to finish off by asking whether there might be some kind of related result for graphs. So basically we've said that critical number in binary matroids, the conjecture is that it's something much simpler. It's just chromatic number for graphs, in a sense. Is chromatic number for graphs really chromatic number for some simple class of graphs, simpler class of graphs, or subclass of graphs? And to make a sort of a specific conjecture in this direction, is it the case that graphs with huge chromatic number admit homomorphisms from Cayley graphs with large chromatic number? I don't know if this is a new conjecture, but it's a new conjecture to me. And be pretty interesting if it was true. If the first conjecture is true, then something like this is true, because you can take the cycle matroid of the graph and then you can find a homomorphism from a Cayley graph into it that's sort of explaining the chromatic number, but it doesn't apply the second thing. The second thing would, this second conjecture doesn't follow from the first, but it's closely related. You're sort of explaining, if the first conjecture was true, you could explain the large chromatic number of one graph from the chromatic number of a Cayley graph, but via homomorphisms that are not graphic.
Jim, is it important that it's Cayley and not like vertex transitive in this conjecture?
There's nothing important in this conjecture. I want, like, anything in this direction would be nice. I briefly had an idea that that any class of graphs that was sort of vaguely plausible might be the right class. So I had a conjecture for a while that was that if you give me a graph with huge, big enough girth and small enough chromatic number relative to your graph, then you get the homomorphism to work. But it turns out the fractional chromatic number blocks you. But my new conjecture is that if fractional chromatic number doesn't block you, then it works. So I always take the sort of the most optimistic road available, and that's kind of what I hope for. So any conjecture along this direction, anything along this direction is something that I would find really nice. All right, so can we? So the real thing is the question. So is it the case that you can take graphs and explain their chromatic number from a nicer subclass of graphs? That's the question. Anyway, I'll leave you with that conjecture. Thanks.
Thank you. Thank you. Let's unmute ourselves and thank Professor Geelen for the wonderful talk. Are there any more questions from the audience? Okay. If not, let's thank Professor Geelen again, and we can leave all the questions during the break.
Okay. It's great to see so many people attending these talks. It's been I think this relay is a really nice thing.
I have actually one question. I was not fast enough.
Yep.
So you mentioned this, you conjectured this generalization of Rödl's theorem to binary matroids, and I was just wondering if maybe it's known for, say, co-graphic matroids or regular matroids or something smaller.
Co-graphic matroids.
Yeah.
Yeah, so co-graphic matroids are they have bounded chromatic number, critical number.
Oh, okay.
So that's actually a theorem of Zhiju's, and that's equivalent to the 8. So basically it's the 8 flow theorem. So it's the same as saying that every bridgeless graph is the union of 3 even subgraphs. So the critical number is at most 3 for every graph. So the critical number of the dual cycle matroid is at most 3.
So probably it also is then true for regular matroids.
Yeah, so it would be true for regular.
Thank you.
Okay, thanks for the question.